This video introduces the basic ideas of SPI communication. SPI stands for Serial Peripheral Interface and is one of a number of common serial communication schemes used in embedded systems. So as the name would imply, SPI is a serial communication method, meaning that as opposed to a parallel communication method where all of the bits are sent at once, in a serial communication method, a single bit or a subset of bits are sent at a time. SPI is a synchronous communication approach. This means that along with the data, a clock is sent to help synchronize between the two or more communicating elements. SPI is set up as a master-slave organization. There is one master in the system. This master, in addition to sending the data that it wants to send, will generate the clock that synchronizes the two communicators, and it is also the party that is responsible for initiating the data transfer. This means that a slave cannot start a data transfer, only the master can. On the slave side, there can be one or more slaves in the system, and a slave is responsible for sending data back as appropriate for the setup. SPI is a full duplex communication scheme, which means that both the master and the slave can send data simultaneously. This is as opposed to some other serial communication schemes where only a single party can send data at any time. And then finally, an SPI, a configurable amount of data can be sent at a time. Typically, this amount of data is either 8, 16, or 32 bits and is usually dictated by one of the parties in the communication and how they structure the data. When it comes to signaling for the SPI protocol, SPI uses 4 wires by default for communication. The first of these is the clock signal, often referred to as the serial clock. This is the clock generated by the master and sent to the slave to synchronize communication. The second signal is often referred to as the master out and slave in. This is the signal where data is sent from the master to the slave. The third signal is the master in, slave out, which is basically the opposite of the master out, slave in. So this is data being sent from the slave to the master. And then finally, the fourth signal is what is referred to as a slave select or sometimes a chip select signal. The slave select is around primarily to tell the slave to prepare to receive data, and if there are multiple slaves in the system, it indicates which slave should prepare to receive data. The slave select signal is an active low signal, meaning that you pull it low to indicate that you're selecting a particular slave. While SPI by default is a 4-wire communications scheme, in some instances you might be able to set it up with fewer than 4. So if you only have one slave in the system and the slave doesn't require it, you might be able to remove the slave select. And if you're either only communicating from the master to the slave or the slave to the master, you might be able to remove one of the other data channels. But this is set up, or this is dependent on your setup. The MOSI and MISO signals are also sometimes referred to by a different name. These also can sometimes be referred to as a serial data in, or SDI, and serial data out, or SDO. And in this case, since it's indicating the direction of the data flow, unlike the MOSI and MISO names where you connect the MOSI signal on both the master and the slave, with the serial data in and out nomenclature, you would connect a serial data out to a serial data in, and so both would have a serial data in and a serial data out. You would just connect them, or the naming convention would be slightly different. So this diagram here shows a case where we have a single slave in the system, but we can also have multiple slaves. This figure here is showing what it would look like if there are 2 slaves in the system. And so with a multi-slave setup, 3 of the lines are connected to all of the slaves. So the clock, MOSI, and MISO signals are connected to all of the slaves. And then for each slave that we have, we need a dedicated slave select signal. So in this diagram, we've got 2 slaves, so that means the master needs to have 2 slave select signals, one going to the slave 0 and one going to slave 1. And so this means that as you add more slaves in this protocol, you need more and more signals coming from the master. Of the 4 signals in SPI, 3 of them are fairly straightforward in their functionality, the 2 data lines and the slave select. In the clocking, there is a number of different ways that this can be configured, and so the specification allows for a bit of flexibility here. One aspect of the flexibility is what is the idle state of the clock. The clock is allowed to be idle either in a high or a low voltage state. And additionally, data can be set up to be captured on either the rising or the falling edge of the clock. And the one caveat to this is that the data must be set a half cycle before it is captured. So depending on how the idle state in the capture is set up, this indicates when you have to change the data on either the master or the slave being sent out on the data lines. And so as an example of what this would look like, if we had a system set up that had a idle high state for the clock and it captured the data on the rising edge of the clock. If we started out with the system in its idle state, this means the clock is idle high. The two data lines, it doesn't matter what's on there because we're not looking at the data, and then the slave select is in a high state because it's not selected anything or it's not active. For the master to send data or to initiate a data transfer, the first thing that would happen would be the master would pull the slave select line of the slave of interest low, and then it would start toggling the clock and setting up the data. So here we've got one clock pulse, and with this setup, we're assuming that data is being captured by both the master and the slave on the rising edge of the clock, and so the data must be set on the previous half clock edge, and so on the falling edge of the clock or just after the falling edge of the clock. This indicates to both the master and the slave that it should set the data. And then in this instance, we're going to assume that we're transmitting 8 bits of data, and so this would basically repeat 8 more times, and so on each falling edge of the clock, the master and slave would change the data, and then they would both read the new data on the rising edge of the clock. And then finally, after all of the data has been sent, the slave select signal would be deasserted to allow other communication to happen, and the clock would stop toggling. And so this provides an overview of SPI communication.